Bismillahirrahmanirrahim. This is our 11th lecture, and here we will discuss what is meant by torque and how a rigid object rotates under the influence of some net torque. What is meant by torque? Torque is the tendency of an applied force on an object to rotate the object about some pivot point. It is a vector quantity and is usually denoted by a Greek letter ta with an arrowhead above it. Arrowhead represents the vector quantity. To understand the concept of torque, we have to consider a bolt which is shown here. It's a bolt with this bolt is pivoted about this point O, and it can rotate about this axis. If we mark the horizontal line as x-axis, the vertical line as y-axis, then this will be our z-axis, and upward direction of the z-axis will be taken as positive z-axis, and downward direction will be marked as negative z-axis. We see that this bolt is in a grip of wrench which is holding this bolt, and whenever we apply a force on this wrench, then force can rotate this bolt about its pivot point O. Let a force is applied at this point, so we mark this point on the wrench as point of application of force. This vector is force vector, and this point is point of application of force, and this point is the pivot point, or the point through which our axis of rotation passes. To understand this torque, firstly we discuss how the direction of torque is located. When a force is acting along this line, then it makes sense that the direction of any kind of rotation of this bolt will be counterclockwise, and the direction of torque can be located by curling the fingers in counterclockwise direction, and this thumb will be pointing the direction of produced torque. So we can fix this counterclockwise direction with positive nature of turning effect. Means torque will be positive whenever the turning effect is in counterclockwise direction, and if this force is reversed in this direction, then the applied force will cause the rotation of bolt about its pivot point in a direction which can be taken as clockwise direction. So again, by curling the fingers of right hand in clockwise direction, we can mark the direction of produced torque, and it will be directed along negative z axis. So we say that clockwise rotation of the bolt about the pivot point causes a negative torque. So these are conventions whenever the torque will be positive or when it will be negative. Now we come to calculate the magnitude of torque. Here we see that this is point of application of force, and from this pivot point or axis of rotation to this point we are marking displacement vector as r, and it is directed away from the pivot point. Its arrowhead is representing this fact. Now we will resolve this vector into its rectangular components, and we'll see that if this angle is phi, this angle is between the line of action of force and this horizontal axis, which was our z axis as well, x axis as well. If this is angle phi, then this will also be phi, and taking this f as resultant vector, we will see that f cosine of phi will be along horizontal. This will be the horizontal component of the applied force, and this vertical component of the applied force will be marked as f sine of phi. We see that f cosine of phi is such a component of the applied force which passes through pivot point or axis of rotation. So we say that the turning effect caused by f cosine of phi is 0. It contributes nothing to the turning effect. The only component of the applied force is f sine phi, which causes the entire turning effect. F sine of phi is responsible for any kind of turning about this pivot point. So to calculate the magnitude of torque, we take magnitude of this vector, displacement vector, and magnitude of this component of force, and multiply both these magnitudes as r f sine of phi. We replace this rf sine of phi by ft, where t is the moment of the applied force. How it was found? As we know that this is line of action of force, and here this is angle phi, and here we say that the angle is of 90 degree. It becomes a right angle triangle, and this component can be taken as height of the triangle. This component can be taken as base, and this vector can be taken as hypotenuse. So this side will be r cosine of phi, this side will be r sine of phi, and this side of triangle will be of magnitude r. r sine of phi is moment arm of this applied force. This is also the perpendicular distance between line of action of force and axis of rotation of the bolt. So we replace r sine of phi by d, and we have tau equal to fd. Here we specify which of the two components of the force causes the turning effect. The only component responsible for this turning effect will be f sine phi, and f cosine phi has no contribution in it. And the rotating tendency tau increases whenever f increases or whenever d increases. It is a convention that torque is taken as positive when the rotation of the object is counterclockwise, and torque or turning effect will be taken as negative whenever the torque is whenever the turning effect is clockwise. If there are more than one force is acting on an object and they all are causing turning effects, then the net torque can be calculated as sum of all the turning effects. Summation tau will be tau 1 plus tau 2 plus tau 3 up to Tn. The SI unit of torque is Newton meter, and it is also the unit of work, but the basic difference between these two quantities is that torque is a vector quantity and work is a scalar quantity. How the direction of torque is found, we have already discussed this, but here we can represent the vector form of torque as cross product of two vectors r cross f. R is a vector, f is also a vector, and we can see here that if an equal vector r is taken at this point, means both the vectors r vector and f vector are joined at this common point, then we can find the cross product, direction of cross product, by rotating the first vector into second. When our first vector will be along horizontal line, r vector will be along horizontal line, then we will keep our fingers of right hand we will keep our fingers on that along that vector r, and we will curl our fingers into the second vector, and this thumb will be pointing the direction of cross product, which will again be along the z axis, positive z axis. Now, before moving to a rigid object, we consider a particle of mass m, which is circulating about some pivot point. This is the path of the circulation, and here it is the central point, pivot point. This is the particle and its mass is m. You see that on a particle there are two forces acting simultaneously whenever it is circulating about some point. These two forces are at an angle of 90 degree to each other. One is taken as tangential force, the other is taken as radial force. Radial force is always directed towards the center of the circle, and tangential force is always tangent at a point where the force is being taken. If this force is to be taken here, then it will be in this direction. If it is to be taken here, then it will be in this direction. So as the point changes, as this particle changes its position, the direction of tangent will be adjusted accordingly. One fact which will be followed, that these two vectors, tangent vector and this radial vector, will always be at 90 degree to each other. Here we know that in case of tangential forces, the net tangential force can be represented as mat, and the net radial force can also be taken as the centripetal force, and we know that centripetal force is m square over r. The radial net force causes the particle to move in the circular path and it has no contribution to the turning effect. The reason behind this is, again, this force is passing through the pivot point through the axis of rotation. This is the axis of rotation, and this force is passing through this pivot point. So it will contribute nothing to any kind of turning effects of this particle. The only force which is responsible for this entire turning effect is tangential force. Summation Ft is causing the net torque, so we can calculate this net torque by taking the net force and multiplying it with the perpendicular distance between line of action of force and axis of rotation, which is also the moment arm. Here the moment arm will be R. So summation Ft into R will give mat into R, as by Newton's second law F can be replaced by product of mass and acceleration. Tangential force will be having tangential acceleration. So tangential acceleration can be replaced with R alpha, as At is equal to R alpha. So summation will be equal to m R alpha into R. Here we will have m R square alpha, and this m R square in this product will be replaced by I. What is I? I is moment of inertia of the circulating particle. As by Newton's second law, we claim that summation F is equal to ma. Here an equivalent expression for angular motion is summation tau is equal to I alpha. So I is serving the same purpose as mass serves in linear motion. I is for angular motion. This sentence is describing that the description in this equation 1 is analogous to Newton's second law, in which we say summation F is equal to ma. Now we extend this discussion of single particle to a rigid object. This rigid object is capable to rotate about this pivot point, and we see that if we mark any of its particle as ith particle and mass of the ith particle is mi and its position is located by a vector Ri. Then by Newton's second law, we can say that this tangential force on ith particle will be having magnitude equal to product of mass of ith particle and product of magnitude of acceleration, tangential acceleration of the ith particle. Now we come to the calculation of magnitude of torque, which will again be Ri into Fi on the same pattern as we discussed in a single particle case. Now we replace Fi by Mi Ai, and Ai is equal to Ri alpha. We see that angular speed omega and angular acceleration alpha for all the particles, for all the constituent particles of a rigid object are same. The tangential velocity and tangential acceleration always depend on the value of r, magnitude of radius vector from the pivot point. Here tau I is equal to Ri Mi Ai. Placing this value of Ai, we will get tau I is equal to Ri square Mi alpha. This is calculation for ith particle. If we take into account all the particles of the rigid object, means if all the constituent particles of this rigid object are taken into account, then the net torque caused into this rigid object under the influence of applied force, external force, will be taken as summation tau external will be equal to summation I tau I equal to summation I. Placing this value of tau I over here, or I square Mi alpha, and we isolate this factor summation I Mi or I square in order to replace it with moment of inertia I. Moment of inertia I will be placed on the despite this factor, and it will become summation tau external is equal to I alpha. We see that for an object of object constituting many particles, we say that summation F external is equal to entire mass of the object into acceleration of center of mass. Here we say that summation tau external is equal to I alpha, equivalent to mass in angular motion is I, moment of inertia, and equivalent to acceleration of center of mass in angular motion is alpha. We say that this equation is equivalent to, analogous to Newton's second law in angular motion. Thank you.